Welcome back to the weekly Dalton Collective Hangout. And today we have rovnys-ricfer, the great, with us today to talk about remote scry. So first off, thanks Rovnys for coming and hanging out with us again.
Thank you for having me.
How's it going?
It's going well. That's probably the best introduction I've ever gotten.
The great rovnys-ricfer. I think so. I think that's what we're gonna have to call you from now on. Okay, so we've invited you today to talk about remote scry. So what is remote scry?
A remote scry is a new protocol that I've just started writing an implementation of. So it's an Urbit to Urbit protocol, network protocol, and so it's a way for two different Urbit ships to communicate, or actually more than two. And it's actually sort of harking back to some of the original designs for Urbit that were referencing Van Jacobson's design of content-centric networking, also called named data network, where basically instead of taking the approach that IP and TCP take, and which is still mostly taken by AIMS, Urbit's normal networking, where there's, each packet is sort of logically identified by who's sending it and who's receiving it. That instead of that, a packet would be identified as either a request for a piece of data or a response to that request, which actually contains the data. Right. So there were, I think in Van Jacobson's thing, there were intent packets and data packets, if I remember the names right. But the idea is that I send, from the implementation of this in Urbit will be like, I want to know a piece of data that is hosted on some other ship, right? Some other ship is storing this data. I want to do a read, right? Like I want to read this data off somebody else's ship, so I can request it, and then so I'll send something like an intent packet, like I'll send a request to read that data, and they will respond with the actual data. This will probably be a one-to-one, like packet for packet, like one request packet leads to one response packet. All right, so this isn't all that interesting so far. There are a couple of things that make this interesting. One is that the idea of named data networking means that this piece of data that's been read can be cached at all the relays that it goes through, right? Like if I request this piece of data, it might have to go through several other ships or other caching nodes in order to come back to me. And those can hold on to it, right? Those can hold on to this response. And that way, let's say that, so this is a way of getting good scalability for any piece of data that many people want to access, right? So let's say that there's, these Dalton Collective videos get really popular, right? And so it's actually, let's say that it's, Kenny, maybe your ship, your planet is hosting this video, and it's under the Dalten star, right? But it just has this video, and it makes it available, over this remote scry networking protocol. And so then when just the hordes of screaming fans all try to download the newest video, your ship only needs to provide this response once, and then its runtime can cache the data for the video. And since in order to access your ship, people have to go through the star, right? They have to ask the star where you are, and the star might be forwarding packets to and from you. And so, but after the star has fielded one of these requests, it can also cache this data. And so now when everybody else starts asking for, your planet's video, those requests don't even hit your planet anymore. The star just has them cached and sends them back, right? And so there are a couple of things in Urbit that make this work particularly well. One is, and they're really kind of part of the same system. So the fundamental primitive is the identity layer, right? The Urbit identity system has Sybil-resistant permanent identifiers, right? So basically, if you're on the network, I can have some reasonable expectation that you're like actually a real person, not one of 10,000 bots in a botnet or 100,000 bots in a botnet. And so because I can have that reasonable expectation, and the idea that actually you're going to hold on to your planet address for a long time, then that's sort of the first part of an identifier, right? There's a stable way to ask for this piece of data. I can say, all right, I want Kenny's planet piece of data. And so the next part builds on top of that, which is that this request for a piece of data is just generally some kind of path, right? Sort of like a URL or a file path. And in Urbit, that will be a scry request. So actually going back also, at many layers of the system, Urbit provides this global immutable namespace, referentially transparent namespace, right? And like, what does that mean? Right, so this is called the scry namespace, named after the function in the standard library that's used to actually perform the read. That's called scry. Right? So I can scry a piece of data, and that means to read a piece of data. And this path format starts with, well, which ship is hosting it? And there are a few other pieces of it, but the other piece that's really relevant is there's a revision number or date. And so the idea is that whenever I ask for a piece of data at this particular path, the Arbo kernel actually guarantees that if it ever responds to that path, it will always give the same response. So this is the idea of immutable. It's like this path, this reference, refers to some piece of data. It will never refer to a different piece of data. The piece of data that it refers to will not change over time, right? It's not like a file on your file system, like on your desktop, where it might have the same name but change the value. No, that's not how this works. You would have to actually increment the revision number, right, in order to actually overwrite the file. And so the reason that this is important is that it means that nobody ever has to invalidate a cache. Right? So if I'm Dalten, right? If Dalten is caching this video, and then people want to ask for the data at that video path, which was maybe it's Dalten, maybe it's video number 37 of the Dalten collective, right? If somebody asks for video 37 of the Dalten collective and the star holds that data, that's always valid. It never has to be told, oh, this homepage is updated. There's different data there. So the caching just works much more seamlessly. Anybody on the network can spread this stuff around. And because these identities are very permanent, this also means that, and we have a public key infrastructure, so I actually know what your keys are. It means that you can sign this video, say, yeah, I produced this video. And so that way, and you actually sign each packet. And that way, anybody who's caching, some packet within the video, if I ask them for it, right, such as the Dalten star, I know that they're not man in the middling. There's no opportunity for a man in the middle attack, right, because I can validate the signature. Right, so there's no opportunity for anybody who's sort of caching this stuff around the network to lie and say, oh, yeah, Kenny said this was the video, but actually it's some other video, right? You can't do like, early 2000s prank, you can't rickroll somebody with this, right? And so okay, so this is the basic idea, right? Is that I can, request some piece of data. That data is identified by this permanent path, this permanent identifier. And anybody who has this data, if I request it from them, they can send it to me. So the very first iteration of this protocol will just be like, I ask you for this. It goes through your star, comes back to me. The star probably won't cache any of it to begin with, just because, but your runtime actually probably will cache it. So, this also means that you can keep using your ship while people are sending these requests in. And those requests aren't competing for CPU with the other stuff that you want to do. Right, and you can have a server that's a separate server that's fielding these kinds of requests. You can separate that out, right? So it gives a lot of nice kind of scalability benefits, performance benefits, if we kind of do the work to actually build those. But there's another piece of it that's pretty cool, which is, um, this actually satisfies a lot of what people like about IPFS, satisfies a lot of what people like about BitTorrent, right? This idea that there could be many people who have pieces of a big file. And so the next stage in this would be to turn this into more of a gossip protocol, where basically I could just ask, 10 random nodes near me, like, hey, I want packet number, like for video 37 on Kenny's ship, I want packets 1 through 100 from you. I want packets 101 through 200 from you, right? And I could just spray those out and get back responses, right? And information could really just diffuse around the network. Christian, you're muted.
Yeah, I was gonna say, I've thought about this like a little bit, like name data networking and so on in the context of Urbit. And like one thing is like name data networking and its like normal sort of description is like sort of pull based. Gossip is like starting to make it like push based, But then I was also thinking about the context of like subscriptions as well. You could do this with subscriptions too, right? Like if say I'm just like even like in just like a normal like chat app subscription, it's like somebody could like cache like the semantic, like cache like maybe like the data and like the semantics and maybe like a certain amount of the effects, and then like that. I don't actually have to go to Dalten to get Dalton's chat messages. They could come through some other route.
Yeah, so I think that there's a fairly long path that we haven't fully figured out between like this sort of very first version of the remote scrying protocol that we're going to build, that I've just started working on, and then something that could be used for subscription data.
Right.
And so like what you're talking about of where, let's say some ship is hosting a chat, and every time there's a new chat message, it just wants to use the gossip protocol to just spray that out to everybody, all of its subscribers, right? That would be nice. But
yeah, definitely a few steps down the line for sure.
Right. So there's a bunch of stuff to figure out sort of in the internals of Arvo and how Gall applications interact with Arvo, right? What that API is between the kernel and user space, to make that so that's sort of a nice, like, principled and ergonomic like way to write applications. But yeah, I mean, I do think it's sort of telling that that is actually most of what we do, and it's actually most of the performance issues that we see in practice, right? So like, for example, the ship, there's a planet that hosts, or the Urbit community group, which has something like 1,000 members, maybe more. 2,000? Okay, yeah, so that's got 2,000 members. So right now what that does is it uses the Ames network, and it just in queues, every time there's a new chat message, it has 2,000 queues sitting inside of it, and it populates, it adds this chat message to each one of those queues. And then, if there are multiple packets in that message, then like every time one of the packets from that message gets acked, that's an event that the host actually has to write to disk, right? So it has to handle all of the stuff in one thread, has to write all of the acts into disk. It's like it really shouldn't have to do any of this stuff. It's just a static piece of data, right? It should have a permanent identifier that people can use to actually pull it. And so so yeah, I think that doing this through gossip, it might sort of be ideal. Where basically, like, I think the gossip version of this is essentially that the host says, here's a scry request and a scry response, right? Here's a response packet, which includes the request. Right? So the response packet has request, signature, and response, basically. So I would just, without anybody even asking for it directly, I would just send that out to all the subscribers, right? Or maybe send it out to like a quarter of the subscribers, and then they ping the other subscribers, right?
I guess like one question here would be like, because like right now it's like not only are you enqueuing it all, you're also uniquely encrypting it for each user, right?
Well, right. Yeah. So I think that what you would do for encrypted data, and of course private chats would fall into this, is I think that you would actually want the encryption key to be tied to the data. And so you would push out the encryption key sort of out of band to people who should be allowed to see the data.
Right.
And so that might be so basically anyone in the group for Urbit community should be able to decrypt, right? But actually maybe there's forward secrecy, right? And so I actually like maybe, you know, every 10 chat messages you rotate the key. Something like that, right? I mean, you can imagine sort of arbitrarily complex ways of doing the sort of key distribution so that groups can actually decrypt the data, and you know, getting kind of different properties depending on what you want. So I think that probably the way we'll build this is to do it in a layered way, where the basic functionality is for unencrypted public data, which is immediately useful for pushing down over-the-air updates, which is actually one of the highest load operations that we do, right? Like, you know, if we have a new kernel update, for example, there might be like dozens of files that have changed. It might be like maybe a megabyte worth of, I mean, hopefully it's less than that, but sometimes, yeah, it might be a megabyte's worth of data that's changed on the host that needs to send out potentially thousands of subscribers. And so, you know, this is the very first thing that once we have a very basic remote scry protocol, we'll just to sort of prove it out, we'll use it for our over-the-air updates. But yeah, that's easier because it's unencrypted. Yeah, for doing encryption, you know, you could also just imagine that there's a group key. That's you know, that maybe the group key changes every time the membership list changes, or every time you delete a member. I think it's actually every time you delete a member, then you have to change the membership key.
Right.
Something like that. But if you tie it to the data, then that cache is better. Right? Because otherwise, every time somebody leaves the group, then you have to like redo the scry responses, something like that, right? Or like redo the requests and responses. So there are a bunch of details there to figure out about how to get the encrypted data to be done sort of in an ergonomic and efficient way. But I think the other thing that's pretty interesting about this is the idea of keeping people honest, right? So one way of looking at this is that because the kernel actually guarantees referential transparency, right? It guarantees this sort of immutability of these paths. Then it should be the case that no one should ever see two different responses on the same request. And if you ever see two different responses and they both have valid signatures, then you should treat it as a Byzantine fault, right? It's like, okay, this person is trying to, or their software, you know, at least is trying to propagate two different pieces of information to two different parts of the network. And they should not be allowed to do that, right? So basically, you know, one of the major features of having a gossip protocol for this sort of thing is that if I ever hear two of these packets, then I should generate a new packet that's a fraud proof, right? So it has, you know, response 1 signature, request, and then also response 2 and signature, right? Just, you know, half of the responses and the signatures. You can fit all that in one packet. I should take that packet and I should flood the network with it. Like, everybody should know if you lie. You know, you shouldn't lie, right? It's like you monkeyed with your software, or, you know, something went wrong. Now, you know, maybe you don't want to just immediately kick them off the network because maybe it was a fluke of some kind, and maybe everybody decides to pardon that guy. You're like, yeah, okay, sorry, like you were doing development on the kernel and like you messed something up, and, you know, like maybe it's a fluke, but maybe it's not, right? Probably it's not. And you know, especially if you kind of fast forward into the future a little bit, let's say people are trying to run, you know, financial software on Urbit, or like software that really is like, you know, mission critical in some sense, right? Or like healthcare data. I mean, any kind of business, anything. Like if you have two businesses that are running Urbits that are interacting with each other, and one of those businesses gets caught running a node that's lying, like, that's a really serious problem, right? That indicates something's been compromised potentially. Right, so I think that as we lean on Urbit more, we'll actually want to take those sort of Byzantine faults more seriously. So then you can kind of you can extrapolate from this in a vague way. I haven't really figured this out completely. So, but I think that there's an interesting kind of way of thinking about, how people can communicate in a sort of trusted way on Urbit, right? It's not exactly a trustless way, but Urbit as a network is designed to engender trust, right? It's actually the opposite of a blockchain in some sense. And so like, let's say that there was, that there was a gossip protocol for these scry responses, and this had been running for a long time, and it was actually just very clear that if you ever hear a piece of data from somebody, like, it's legit. Like, Byzantine faults get caught really quick. Nobody's tried one in a while, because the last 20 people that tried them got caught in like 10 seconds, and nobody, and then their ships were never heard from again, right? So then that actually gives you this way of, the other thing is that because you can look at the totally ordered sequence here, right? Like, somebody can post a totally ordered sequence, right, of data. And then you could know that there weren't missing pieces of that, right? Because of this, Byzantine fault protection, right? It ends up looking like anybody can kind of publish their own personal blockchain, many of them actually, right? That could sort of be validated to differing degrees depending on how much you actually care about the data, right? But I think the basic thing that would be that if you typically publish something within some group, some private group, right? So like, there's some state that you're tracking, some maybe sequence of transactions that you perform of some kind, right? So you could take those and you could actually publish those with this gossip protocol out to a group, and maybe there's a shared agreement that everybody shares all these things within the group, and they validate this. And so let's say that you have some let's say that somebody starts some group that does that's doing some sort of asset exchange, right? And there's a sequence of assets that each person's of transactions that each person has performed, right? So the whole group that's participating in this exchange, that is the exchange, right? They could all gossip these things out, and sort of keep them keep everybody else honest. And then you could also, because they're all, that group is sort of like one like one sort of network within many networks within the Urbit system, right? Like, that'll also have overlap with other groups. And so you can imagine these things actually sort of, deciding that if I hear, from this other group, some crypto exchange group, let's say, some asset exchange group, maybe I fire requests in to check with, 10 of them, and they all say the same thing, right? So I guess their gossip protocol is working, right? Then maybe my group, I'm in another one of there, and then those two groups could actually start to trust each other. So you could get sort of like an internetwork, like an internet, right, of these sort of trust, these sort of webs of trust. So you have an internet of trust, I guess, is the idea. And you could actually use real consensus protocols to back this too. I think the one that's probably most appropriate is the Avalanche protocol, because it's very minimal and it supports a very large number of validators, and the latency is relatively low, right? And it's pretty easy to, I think it'd be pretty easy to write for Urbit, to write an implementation of that protocol, especially since you already get the Sybil protection from Urbit. So you could basically, let's say that if you have a social group, like some sort of asset exchange group on Urbit, I don't think that you would need to I think the validation cost would actually be so low that that would just be sort of like how the app works. Like you'd write a Hoon app to participate in this exchange, right? This sort of like decentralized exchange here, which is just an Urbit group, and that app by default would validate everybody else's transactions and store the state, right? And so everybody would validate every transaction, and I don't think you would even need these sort of more complex staking games where you have to try to incentivize somebody else to run the transaction. It would just be, yeah, you turn it on by default, and you'd have to put in a fair amount of work to like not actually do that. Most people wouldn't bother, and plus, like, it should just be something you don't even really notice. It should be pretty, a low performance overhead and low data overhead.
You could do that, I think, kind of like a payment channel, right? Like you could have like basically it's just like for each like block or each transaction you bump the sequence number, and you have all these people signing it, and then like anybody could like you just have like a hash time lock contract on chain, and anybody can like like publish like a hash to exit, and then they also like publish a transaction that's like, hey, like I'm closing this, or I'm closing my position here,
Yeah.
and then that's what you publish on chain, and then everybody has like 24 hours, 2 days, however long, to like publish a proof that didn't happen or whatever, that like that whatever, and it's like that, or like like I don't know, I don't know how you would do it for like instant finality, because you'd like kind of need everybody's signatures, and then that gets costly. But yeah, if you do like a hash time lock contract and just do it like if there's no negative proof, then like people can close their positions and exit to another blockchain.
That's interesting.
You could also use this as some sort of multi-sig scheme. So you can imagine I have half a signature, meaning there's like a 2 of 2. And I do this protocol, I'm doing all kinds of stuff, and like similar to what Christian was saying, I want to close it out. Well, maybe that's a request to somebody else who needs my signature and their signature. They do something else out of band, like settling on a blockchain. And that all sort of interoperates with other chains. So you could use you could have a key that's in Urbit that's more secure, because if it ever gets compromised, you still need somebody else's key in order to do something.
That's a cool idea. Yeah, so you could basically use Urbit as a way of getting sort of social recovery for a key, or like or social multi-sig, and you could use that to automate the process too, right? So like, yeah, okay, you have one of the shards lives in my Urbit, one of the shards lives in your Urbit, and so like together we can sign a transaction.
Yep, and it's just like we do that for each other's benefit.
Yeah.
Hopefully, maybe more than just 2, because maybe some additional redundancy.
Well, I mean, yeah, you could also imagine like you have some group that has a known fixed membership, let's say, and it could even be quite a few. But then you could do you maybe, in order to get that group to sign off on something, like you ask each node to sign off on it. And then each one does a Schnorr signature, and you aggregate all the Schnorr signatures. And once you get a majority from the group, then you're like, okay, I guess this group says that, right? And so you could actually have different Urbit groups like asking each other for to sign various things. And you could at least aggregate the signatures that come out of that.
Cool. And so Ted, you've also mentioned that this is something you're kind of working on now. Can you give us an idea of like kind of where it is in the priority sort, and kind of how much effort and time you're thinking it might, for some of these features, to might pop up in front of a user?
It's definitely my highest priority. Well, okay, so it's the second highest priority of my personal, work at Talon at the moment. The highest priority is that I'm working with our security auditors, because we're working to get that done by the end of the year. But that's not a full-time thing, because it's mostly they're security researchers that are doing their thing, and they periodically ask me some questions.
Have they learned Tune?
You know, they've learned Hoon a lot more than one might expect, and it makes me think that a lot of the people who haven't learned Hoon, it's because they didn't try that hard, you know, or they didn't like it for some reason. And it just makes me think that, like, you know, that if people are being paid to learn Hoon, they'll learn it real quick.
Yeah, no doubt.
Yeah, I mean, within, I think, a day of encountering Urbit, maybe 2 days, one of the researchers was able to pull up a Dojo shell, take a packet capture, you know, deserialize the packet, retrieve her private key and somebody else's public key out of jail from the dojo, use those to like construct a symmetric key, use the symmetric key to decrypt the packet, take the packet, deserialize it, look at all the different like components of it, figure out which flow it was on with the names, right? Like within like 2 days. So
Okay, that's pretty good. That's impressive.
so yeah, like I don't want to hear about how difficult Hoon is anymore. Like but yeah, no, I've been very pleased with them. I think that they have a they picked up, you know, the Urbit design very quickly, and I'm learning quite a bit from them actually about things like how to prevent DDoS attacks and other things like that, because that's, you know, that's something we're going to have to work on the next year or so probably, is actually hardening Urbit against various kinds of network attacks.
Is like the runtime being like audited?
Say that again. So you broke up.
Is the runtime being audited?
No, just the architecture names.
Okay.
The yeah, so I don't know. We might want to do another security audit later for the actual runtime. I don't know exactly what approach we'll take for hardening that and sort of guaranteeing its hardness. We might be better off doing like a, you know, a 0-day bounty program or something. But that's sometime in the future. For the moment, don't put your valuables in Urbit. Public service announcement. The runtime has not been hardened, and it will need to be hardened. So that's my number one priority, but it's not it's not taking that much of my time. And then this is writing the first implementation of the scry protocol is next highest priority. So that it's mainly what I'm working on. I have a little bit of forward work to do also, but mostly I'm working on this. So I'm hopeful that like, in maybe, I feel like I should be able to have something that can like that can send and receive packets in maybe like a couple weeks, and then something that can send and receive packets in a less dumb way in like maybe a week or two after that, and then something that's sort of relatively complete that does routing correctly, maybe in another week or so after that. And then I think before really like pushing this out and starting to use it in earnest, I want to also write a caching layer in the runtime, so that just a very basic cache, and then take probably like a week and maybe two, and to write an integration with Clay, so that when Clay goes to retrieve a file from some other ship, they'll actually use this remote scrying protocol. So, you know, I'm hopeful that I can have something by basically the end of the year. You know, it'd be great to have something like before the Christmas break. We'll see. I don't know exactly. It might take a little longer. It might be shorter.
And then, like you said, the likely first use case would be for delivering OTAs faster or better.
Yeah, that's going to be the first application of this protocol, and really the one that we'll use to test it out. So, and this won't be. So the first version won't have any facilities for encryption, and it won't have any facilities for caching at intermediate nodes, or like relays won't cache, and and then also it won't have any sort of gossip facilities, and it probably won't do any fraud proofs.
Okay. One last question, and that you said that the cache would likely be in the runtime. Does that mean whatever's being put there is not going against your sort of 2 GB limit?
That's right. Yeah.
Yeah. Okay. Great. And that would also, like you said,
it'll probably be living in the other process, right? There's the worker process, the daemon process. So the worker process is what runs knock. There's a 2 GB limit for stuff that's inside of your Arvo state. But then the other process is what handles I/O. So basically, incoming packets, like scry request packets, will be handled there, and the cache will probably live there, so that it doesn't have to do inter-process communication to ask the worker to handle the request. And it'll just fire off the packet, the response packet directly if it has a cache.
Which also means you can continue to use your Urbit while this is happening.
That's right.
That's nice. Great. Cool. Christian, any other questions? Anyone else?
Not particularly on this topic. I mean, there's like a semi-related question I would ask, but I'd wait.
Cool. All right. So I guess we'll go ahead and record or end the recording there. But yeah, Ted, thanks for coming on.
Sure. Thanks for having me.
Yeah. Thanks everybody for showing up.
There is something I want to ask Ted though.